On this page, we will use the sampling distribution as a probability model to lay the groundwork for inference about a population mean. As before, we can always use a simulation. However, we can also use a normal model when conditions are met. The sample size is large if n is greater than 30, or if the variable is normally distributed in the population. As we've done before, we convert the statistic, in this case the sample mean, to a z-score and use a standard normal curve to find probabilities and identify unusual sample means. So we'll again use the normal distribution calculator. We're allowed to use this even though now we're talking about quantitative variables as opposed to categorical variables and sample means as opposed to sample or the population proportions. So still the same one. Let's look at an example and we'll actually use that applet. We'll look at surprising heights for individual basketball players. Suppose we have a population of adult male basketball players and we know their heights. The mean height is mu equals 190 centimeters, and the standard deviation of their heights is sigma equals 7.2 centimeters. The heights are normally distributed, which is often the case with body measurements. Would it be surprising to find a randomly chosen player from this population with a height of 195 centimeters? We can answer this question by computing the probability that a randomly chosen player from this population has height greater than 195 centimeters, the probability that x is greater than 195. First thing to note is that heights are normally distributed in this population, so we can use the standard normal curve to estimate the probability. The second thing we need to do is convert the interval x greater than 195 to an interval of z-scores. So recall that the z-score of an x value is the number of standard deviations that value is away from the mean. So the formula is that value minus the mean, that's the distance from that value to the mean, divided by the standard deviation. So the x value 195, as you see here, minus the mean, mu, which was 190, over sigma, the standard deviation, 7.2. In the numerator, 195 minus 190 is 5. 5 divided by 7.2 is about 0.69, so that'll be our z-score. This tells us that the interval of x values, x greater than 195, corresponds to the interval of z values, z greater than that z-score we calculated, 0.69. So the area beneath the curve for the interval of x values should be the same as the area under the curve for that interval of z-scores. And we have that standardized, so we know how to do that with the applet. So let's scroll down and look at that applet here. So if we type in a z-score of 0.69, we should be able to find the area to the right of that value. So remember we said, don't press enter on your keyboard because the applet doesn't like that. You have to press the enter button here. So it looks like the area to the left, that's not what we want because we want to know what's the probability that the height is greater than, those are the values on the right side, the larger ones. We don't want that. We want this other one. The area to the right of the z value is 0.245. Okay, we'll bring that down to where we are here. Okay, so as they say here, we found that the probability that x is greater than 195 is the same as the probability that a z-score will be greater than 0.69, and we found that to be, by using the applet, 0.2451. In conclusion, this probability is fairly large, almost 25%. If you change that 0.2451 to a percent and move and round it, we conclude that it would not be surprising to find a randomly chosen individual basketball player from this population with a height of 195 centimeters. Now revisiting that example. As before, suppose the heights of individual players are normally distributed with mu equals 195 centimeters again, and sigma is 7.2 centimeters again. Would it be surprising to find a randomly chosen team of 25 players with a mean height of 195 centimeters? This time, the probability model is a sampling distribution. Here's what we know about the sampling distribution when n equals 25 players. First, the distribution of sample means is normal, even though our sample size is less than 30, because we know the distribution of individual heights is normal. If the individual heights were not normally distributed, we would need a larger sample size before using a normal model for the sampling distribution. Secondly, the mean of the sampling distribution is 195 centimeters, the same as the mean of the individual heights. I think we said that. The mean of the sampling distributions of these quantitative variables should be the same as the mean of the total population. The standard deviation is different though. The standard deviation of a sampling distribution is, as we talked about, sigma over the square root of n. So the standard deviation divided by the square root of the sample size. In this case, they said sigma was 7.2 divided by, we said that we're using a sample size of 25 players, so square root of 25 in the denominator. 7.2 divided by the square root of 25 is 5. 7.2 divided by 5 is 1.44. As before, we also call the standard deviation of the sampling distribution the standard error. Now we can answer the question by computing the probability that a randomly chosen player from this population has height greater than 195 centimeters. In other words, probability that x is greater than 195. Sample means are normally distributed, so we can use the standard normal curve to estimate the probability. We convert the interval, the sample mean greater than 195, to an interval of z-scores. So note that the z-score is the number of standard errors the sample mean is from mu. So the z-score calculation for the sampling distribution uses mean 190 and standard error, now not just sigma, but sigma over the square root of n, 1.44. Now we'll calculate the z-score with those. As they illustrate here, z-score is not just the difference between your, and before in the previous example above, we did capital X minus mu over sigma, but now it's not capital X, we're looking at the sample mean, X bar minus the mean of the population over the standard error, but the standard error is not just the standard deviation, it's the standard deviation over square root of n, standard error. Okay, and that calculation is a little more complicated. We did see above that sigma divided by the square root of n is 1.44, so that's our denominator, 1.44. The numerator is still 195 minus 190, because that's the population mean minus the sample mean. If you divide those, you get 3.47. Therefore, the interval, the sample mean x bar greater than 195, corresponds to the interval where z is greater than 3.47. That's z-score is usually, I don't know if you noticed from the examples we've done, they're usually between 0 and 2, usually, but I think a z-score of 3.47, that's fairly rare. That's very large. As you can see, they've outlined the z-score here with a yellow bar, and we're looking for the area beneath the curve here where I circled. It doesn't even look like there's any area there. It's going to be very small. And if we use the applet above, we'll see that we want to calculate z, for z equals 3.47. What's the area to the right of that? Let's scroll back up and see that. Okay, where was that applet? Here we go. Was it 3.47? I'll press enter. So you see that the area to the left is not what we want, because we were interested in what's the probability that the height is larger. Larger is greater value, so we want the larger values. 0.0003, 3 zeros before the 3 and behind the decimal. So where do they have that? Oh man, get lost in here. Here we go. So the very end. All right. So we have found that the probability that the sample means are greater than 195 is the same as the probability that the z-score is greater than 3.47, which using the applet we found to be 0.0003. And if you move that decimal over twice, you still have just 0.03% chance. That's not even 3% chance. That's not even 0.3% chance. That's very low. This probability is very low, much, much less than 1%. We conclude that it would be very surprising to find a random sample of 25 basketball players from the population of total basketball players with a mean height of 195 centimeters. It's interesting to notice that the height cutoff we used in these two examples is the same, 195. When considering the individual, we concluded that finding a randomly chosen individual with height of 195 centimeters would not be surprising. However, when we considered the team, we concluded that it would be very surprising to find a random sample of 25 players with a mean height of 195 centimeters. This makes sense because as sample size grows, variability shrinks. Here we considered a sample size of 1 versus a sample size of 25.